Okay. Well, thank you, Quack, and thank you for the invitation. It's really a pleasure to be here. My first time in Singapore. So what I would like to tell you about is demonstrations, really, of algorithmic quantum speedup, which I'll define. This is based on 3 papers, one that was published last year, and 2 more that are now in the archive, and plus I'll reference some older work as well. But let me start by motivating this, if I can get, yes, there we go. The topic in terms of this question of that is on all of our minds, what is the utility of the NISQ era, era of noisy intermediate scale quantum computing? There's maybe no better place to start to read about that than in this very nice paper in RevMod Phys with authors whose names should be familiar to you, including our generous host. This is the context for this talk, but more specifically, what I would like to talk about is quantifying this utility via a hierarchy of quantum speedups. So I'm going to define this hierarchy: limited algorithmic quantum speedup, just algorithmic quantum speedup, and unambiguous algorithmic quantum speedup. I'm going to start by defining what I mean by these terms, and I will attempt to convince you that we have demonstrated this last element in the hierarchy here. So what is a limited algorithmic quantum speedup? What I mean by that is that you can solve a computational problem by running a quantum algorithm on some quantum hardware and demonstrating a quantum speedup over the best available classical algorithm. And the point is that we often don't know what is the best classical algorithm, so that's why it's available, and that's why this is just a limited algorithm quantum speedup. If you can't prove it, you just benchmark against the best that it's currently known. That's the case of a limited speedup. Now, a better case, or actually before we go to the better case, I should say that this includes all the recent examples of quantum advances in both quantum simulation and quantum optimization. So, for example, the recent paper by IBM on the evidence of utility, as well as a recent paper by D-Wave on computational supremacy in quantum simulation, as well as examples of quantum optimization from Lucan's group, and also the paper that I hope I'll have time to talk about. These are all examples of limited quantum speedups. Now, next up in the hierarchy is just algorithmic quantum without the limited caveat. So here, what I'm talking about is where we can demonstrate a speedup against the best possible classical algorithm. But there is a caveat here as well, which is that the speedup is demonstrated subject to some assumptions, very reasonable assumptions, like P is not equal to NP. Okay, but nevertheless, assumptions. So that includes well-known examples such as quantum supremacy and quantum advantage in quantum machine learning. The work from Google, of course, and more recent work from Caltech. And then finally, at the top of the hierarchy, we have the case of an unambiguous algorithmic quantum speedup. So here, not only do we demonstrate an advantage against the best possible classical algorithm, but we don't introduce any assumptions or conjectures whatsoever. So this is as pure as it can get. So the goal of this talk is to convince you that we have the first demonstration of such an unambiguous algorithmic quantum speedup on quantum hardware. And of course, there's some price you have to pay in order to make such a statement, and that is that this will be done in the context of oracular or black box algorithms. But to be fair, we're going to price in the cost of constructing the oracle. Okay, so that's the plan for the first 2/3 of the talk. And then in the last third, if I have time, I'm going to talk about a demonstration of a limited algorithmic quantum speedup for optimization. Okay, so first I want to get a little more quantitative about what I mean by a quantum speedup. The metric I want to use to quantify a quantum speedup is the time to solution metric. This is a very natural metric. The time to solution, the TTS, depends on the problem size n and the runtime, T sub r. And it's simply the ratio of the two. So the circuit runtime is TR. So obviously the time to solution is how long it takes you to run the circuit, but the circuit only succeeds with some probability. So you want to divide by the probability. Okay, so if the probability is 1, then it's just you run the circuit once. If the probability is very small, then you're going to have to repeat the circuit many times before you get the right answer. So this should be completely obvious to people who are practice quantum algorithms, but of course, a quantum speedup is not a constant factor, a constant prefactor, right? Like 100 times faster. That's not what we're interested in. We're interested in scaling. So we're interested in quantum advantages that grow, where the advantage grows as a function of the problems. The best case, in some sense, is an exponential speedup, where the time to solution in the quantum case is polynomial, but the classical is exponential. That would be an exponential speedup. Or we can have a polynomial speedup, where in both cases we're talking about polynomial time algorithms, but the quantum exponent is less than the classical one. That's polynomial speedup. Or we can compare two exponentials where the quantum exponent is less than the classical exponent. So that would be another example of a polynomial speedup. We'll define a quantum speedup as an advantage in the scaling of the time to solution with the problem size, even if the classical time to solution is smaller overall. Right? So if the classical time is, let's say, 1,000 times smaller, but the slope, the scaling of the quantum algorithm is better, I'm still going to call that a quantum speedup because we're interested ultimately in asymptotics. Okay, so that's the context. So now I want to talk about the first paper, and this is work that was done with Vivek Pocharel, who was a graduate student in my group, and he's now at IBM. And so the problem that we're going to talk about is literally a textbook problem in quantum computing. It's the Bernstein-Vazirani algorithm with a twist. And the twist is the single-shot version. And so this is the problem. You can think of it as a game. The game is to guess a certain secret bit string B of n bits. By the way, if anybody has a picture of Ethan Bernstein, please get in touch with me, because I have looked for one for a long time now, and I just can't find it. So this algorithm is one of the very earliest examples of a theoretical, unambiguous algorithmic one. And here, to remind you, here is what the problem is, and I'll also tell you what the single shot twist is that we have introduced. So you have an oracle, and you need to guess a secret bit string B that only the oracle knows. So you give it some guess X, which is a bit string, and it returns B dot X mod 2. Right? So it returns a single bit, the inner product modulo 2, the secret string and your guess. So the original Bernstein-Vazirani problem, the secret string is fixed, and then you can solve this problem in n guesses, because every time you get a new bit, and you can just systematically get one bit at a time. But what we want to turn this into a problem that's exponentially hard, and so we modify it in a very simple way. We just change the bit string every single time, the secret bit string. But nevertheless, you're still allowed just a single guess. And so the rules are that you guess the bit string, you win if you correctly guess B, but you lose otherwise. And if you lost, well, then a new bit string is selected, and you start over. Okay, so because you're only getting one bit, classically, every time you guess, there are n-1 unknown, right? And so that means that the probability that you're going to succeed is going to be exponentially small, 1/2 to the n-1. So P sub s is the probability of success, correctly guessing the bit string, after you've only learned one bit from the oracle. Right? So the probability that after you get that one bit, that you will then correctly guess the bit string is exponentially small. And in terms of the time to solution, so the classical time to solution, remember the time to solution is the time it takes to run the circuit, which is n in this case, because the oracle still has to add the bits in order to compute b dot x. That takes time n. Divide that by the probability of success. And so classically, it's going to take you n times 2 to the n-1 on average to find the correct bit string. So this is exponentially fun. Now, the Bernstein-Vazirani algorithm starts by putting n qubits in the 0 state, another qubit in the 1 state, then creates a superposition, and then it runs this oracle, which is basically do a control knot between every qubit and the ancilla for every one in the secret bit string. Right? If there were a 0 here, then let's say in the first position, then you would not do the control knot from the first qubit to the ancilla. And then you undo the superposition and you measure on the computational basis. And if this circuit were to run perfectly without any noise, you would find the correct bit string with probability 1. This is what Bernstein-Vazirani showed. So the quantum time to solution is n, because the depth of the circuit is n, the number of C-naughts. I'm ignoring the Hadamards, compared to the classical time to solution. And so you see there's an exponential speed up here. However, in reality, of course, every gate and measurement is imperfect. And let's ignore the measurements and let's just talk about the gate fidelity. So the gate fidelity is multiplied. And because the circuit depth is n, the n C-naughts that you have to apply to construct the oracle, that means that the expected success probability is going to be exponentially small, right? With some factor here, lambda, a positive number, which quantifies the noise. And so this is a very simple back of the envelope estimate of the success probability. And that means that we're not going to get an exponential speed up. So something else is going to happen. We can define the speed up ratio. So if I take the classical time to solution divided by the quantum time to solution, it's the ratio of these two quantities, right? So the actual speed up ratio is 2 to the 1 minus lambda, this noise parameter, lambda times n. Another way to write this is the quantum time to solution is the classical time to solution to the power lambda. And so you see that you're going to win, in the quantum case, you're going to win if lambda is less than 1. Okay, so if this noise parameter is less than 1. I'm not talking about error correction, right? So there will be error suppression that will come, but these are NISQ algorithms. So I'm absolutely not excluding the future use of error correction, but right now in the NISQ era, error correction is not quite feasible. Okay, so remember this parameter lambda because it's going to play an important role. So lambda is a very crude way to quantify the noise, right? If lambda were 0, then the circuit is running perfect. For any value of lambda greater than 0, there's some noise, and for lambda less than 1, we expect to see a quantum advantage, a polynomial quantum advantage. Okay, so this is the simple theoretical background here. So now we want to try this experiment on IBM. And this experiment was done a few years ago. So this was back when IBM had these 27 qubit machines. In particular, we picked 2 of them, Montreal and Cairo. This is just the layout. And I want to highlight a couple of noise parameters that are relevant here. So Montreal has had a slightly higher quantum volume. And it had a slightly lower 2-qubit gate error than Cairo, right, by about a factor of 3. But it was a slower machine. The readout duration, which dominates the total time here, was a factor of 5 or so larger than for Cairo. Okay, so overall higher gate fidelities, but a little bit slow. Okay, so now we're going to implement this Bernstein-Vazirani algorithm on IBM. And let's see what happens. So the first thing to try is to fix the problem size. So n equals 6. And so we're talking about Bernstein-Vazirani with, in this case, with bit strings of length 6. In this case, there are 64 possible secret strings, which correspond to 64 different oracles. And here are the experimental results for Cairo. Oracle number versus the actual detected state, and this is sorted by increasing Hamming. Right, so the most C-naughts are over here, and the fewest are over here. And what you're seeing is that the probability of success is color-coded, and it decreases in proportion to the Hamming rate. Right? And there's some off-diagonal noise here, which you might be able to make out. So why is that? Well, this is simply consistent with deeper circuits having more decoherence, right? So again, increasing Hamming weight means that there were more controlled knots in the circuit, and so deeper circuit, lower success probability. Okay, but how good are these results? Well, it turns out that if you average over all the oracles here, over all 64, then the average success probability was still 72%, which is not so bad. In fact, it looks really great compared to the classical success probability. The classical success probability was 1 over 2 to the n minus 1, or 2 to the minus 5, which is only 3%. Right? So naively, you might say, hey, this is an example of a quantum advantage. And we're succeeding in this n equals 6 Bernstein-Vazirani problem with much higher success probability than we could classically. So is this sufficient for claiming that there's quantum speedup? And the answer is no, because you have to look at scaling. Right? So it's all about scaling. And if you actually continue the experiment for different problem sizes, so here's the time to solution on a log scale versus problem size. So there's a lot going on here. Let me explain. These white background lines, that's the classical scaling. So what we want to beat is the slope of the classical white line. And that's, so here, right? And there are two curves here. One is the Montreal data, one is the Cairo data, and then there's also what we'd expect if we had an ideal noiseless quantum computer. So what you're seeing is that the scaling for both Montreal and Cairo, both of these machines, the asymptotic scaling, to the extent that we can extrapolate, it gets worse. It is worse than the classical scale. All right, so even though at n equals 6, we got a higher success probability in the quantum case, the scaling, which is what we're interested in for quantum speedups, is worse. All right, so actually, this is an example of a quantum slowdown, not a quantum speedup. And actually, it's even worse than that because we couldn't get any success probability, any correct answer beyond these points indicated here. That's why these curves terminate. Right, so in 10,000 shots, there was never a correct bit string identified beyond these problem sizes here. A little worse for Montreal than for Cairo. Okay, so this is very discouraging, right? So we're getting a quantum slowdown, not a quantum speedup. Okay, so what are we going to do? Well, if we could, we would do quantum error correction, but we can't. By the way, this is going all the way up to the largest size possible. Right? So we tried this all the way up to 27 qubits. Remember the Bernstein-Vazirani algorithm, you need n plus 1 total qubits. So that's why it's only going up to 26. These are 27 qubit machines. So quantum error correction is out of the question. But what we can do is dynamical decoupling. So let me give you a very quick primer on dynamical decoupling. And here's a simple illustration. So suppose that we have a system-bath interaction that corresponds to dephasing, which is a good model for some of the noise on the IBM machine. And let's implement, let's look at what happens for a single qubit. We're going to implement this evolution. It's going to be free evolution, so that's defined here. Free evolution is evolution subject to the system-bath interaction and the pure bath Hamiltonian. And that will be followed by an X pulse, free evolution, and an X pulse. And an X pulse is this. Right? So this is just a pi pulse about the X axis. So if you do that, after you prepare a qubit in a superposition in the XY plane, so the free evolution is this. Okay, you evolve for time tau. Then you apply the X pulse, and that flips the state over to the other side, about the X axis. Then again, free evolution by the same amount of time tau. And then another X pulse, and it takes you back to where you start. Right? So this is the simplest dynamical decoupling pulse sequence, the so-called XX pulse sequence. You see how it undoes the effect of the free evolution, the decoherence due to the interaction with the bath. Okay, so this is the schematic that probably everybody knows. But just to take it a little bit further, let's talk briefly about a more general version of this. So how do we generalize from the XX pulse sequence? Well, if you're given some arbitrary system-bath interaction, how do you, in general, choose a pulse sequence that suppresses that system-bath interaction? And you can do this using symmetrization. So here's, again, is the free evolution. The free evolution is evolution for time tau subject to the system bath plus the pure bath Hamiltonian. And we can include a system drift term like crosstalk in HSV. And then to generalize the XX example, let's choose a group of unitary operations. So G sub J. Let's let G0 be the identity operator. And the idea of symmetrization is that for this group, we're going to cycle over all the elements of the group. So the unitary at time capital T, which is k times the pulse interval tau, k is the order of the group, is going to be the following cycle. Right? So we're start from G0, conjugate by G0, conjugate by G1, and so on and so on. And we can write this as a product, and then we can move the G's up into the exponential, right? So you get this expression. And the G's act only on HSV because they are, the G's, I should have said, are pure system operators. So the G's are operations we apply in the system, just like we did with the XX sequence before. And now we can use the BCH formula and expand this to first order in the total time T. And so the first order term can be written in this way, where HSV prime, the effective system bath interaction, that is just the sum of all these conjugation operations. And so this is the group averaged effective Hamiltonian. And we'll get first order decoupling, first order in T, so ignoring the order T squared term, if we can choose the decoupling group, capital G, such that this is zero. That will correspond to having averaged away the system bath interaction. Right? So in this case, this ignoring order T squared terms, the overall unitary is just the identity operation, just like I showed you in the example on the previous slide. Right? And it turns out that this can always be achieved. For any given system bath interaction, you can always find such a group G, which will accomplish this. And for example, if we're talking about a single qubit, the most general system bath interaction is just the sum of the Pauli terms. Right? And if I cycle over the Pauli group, that is the appropriate group in this context. If I cycle over the Pauli group, which is what's written here, identity X, Z, Y, I get the so-called XY4 sequence, a very well-known sequence in the NMR and dynamical decoupling community. So this XY4 sequence, just multiply the X's and Z's here to get a Y. This sequence does the trick. It makes the effective system bath interaction zero for any arbitrary single qubit system bath interaction. And this is much more general. In fact, this can be done for any arbitrary system bath interaction. You can always find a group. How large the group is and how long it's going to take you to decouple, that's a separate question. Right? So in the most general case, if you have n qubits and you consider the most general system bath interaction, you need a group that is exponentially large. So it's going to take you an exponential amount of time to perform this decoupling. So I'm not saying that it's always efficient. Of course, it's not. But in the case of if you're only trying to decouple single qubit terms, then it is efficient. Okay, so this was implemented, and already in 2018 we had the first dynamical decoupling experiment on IBM. So here what you're seeing is for this old quantum device that IBM built back then, the IBM Q16 Rushlicon 16-qubit device. Here is the fidelity averaged over the states that are written here, 30 random initial states plus the 6 Pauli eigenstates. Here's the fidelity as a function of time. And the black curve is what happened if you just did free evolution. So no dynamical decoupling. And the red curve is what happened back then when we applied the XY4 dynamical decoupling. See how we're able to, back then, we were able to improve the coherence or the fidelity decay time by a factor of 6. And this little oscillation here that you see, this damped oscillation, that turned out later that was due to crosstalk that was discussed in this other paper. And that crosstalk oscillation, which is a drift error in the system control Hamiltonian, is removed by dynamical decoupling. This is a non-Markovian effect, and dynamical decoupling removes non-Markovian noise to some order. Okay, so XY4 is absolutely not it. There are much better sequences than that simple sequence. And in fact, there are sequences that exhibit what I would like to call fault tolerance, because basically there are advanced sequences that are robust to intrinsic pulse errors, which is the kind of thing that you want to do in fault tolerant on computer. And moreover, not only do we have sequences that are robust to their own errors, we can design sequences that go well beyond first order decoupling. In fact, we can achieve dynamical decoupling to arbitrary order in perturbation theory. The XY4 sequence is good for first order decoupling, but we can go to nth order decoupling. Sequences are known. So we had a paper last year that did a detailed survey of many sequences that have these properties. But what I want to highlight is one particular sequence, which is known as the universally robust sequence, or the URN, and I'll explain the N in a second, which was discovered by Genov and collaborators. And this sequence, I don't have time to go into much detail, but what I'll say about it is that it achieves order n/2 cancellation of pulse errors, meaning the fidelity goes like 1 minus epsilon to the power n/2, where epsilon is a measure of the pulse error, using only n equally spaced pi pulses. And those pi pulses, somewhat similar to XY4, you have to choose different axes, except the axes are not simple x and y, they make some angle phi sub k with the x-axis, right? So here's for example, is UR6, the n=6 member of this family. And so you start with a pulse along the x-axis, then a pulse that makes an angle 2 pi over 3 from the x-axis, do a pi pulse around this axis, and then again, x-axis, again 2 pi over 3, and so on. Right? And just to show you in an experiment how well this works, here is a more recent example of just trying to preserve a state. So this is the fidelity, again, averaged over 30 random states plus the 6 poly eigenstates. Sorry, actually, this is just the minus I. Just trying to preserve the minus I state here. And so here is the performance of the UR20, order 20 in this family, compared to free evolution, which is the red, and then CPMG, which is a standard sequence from NMR, and XY4, which I already talked about. And you see how the fidelity, right? So what is going on with these UR sequences? Here's a little animation to show you in what sense they're fault tolerant, robust to their own imperfections. So forget about decoherence for a second. Let's just say that we have pulses that have axis angle errors. So instead of being along, let's say, the x-axis, it's the x-axis plus a 5-degree error, as well as over-rotation or under-rotation. So in this example, it's a 15-degree over-rotation, 5-degree axis angle error. So if you're running the XY4 sequence, and the goal is just to implement the identity operation, that means I'm going to run this sequence, and I would like this arrow at the end of the sequence to point to the exact same point. But here's what happens when you apply XY4 with these kind of intrinsic errors. So it does a nice trajectory on the ball sphere, and it ends up not at all here, it ends up down here. But if you apply the UR6 sequence, which I showed you on the previous slide, with the exact same intrinsic errors, so you'll see that it has a really nice fault tolerance property. So it does a different trajectory on the ball sphere, and it ends up almost exactly, it's not invisible to the naked eye, almost exactly where it's supposed to be, even though it had these 15-degree over-rotation and 5-degree axis angle error, right? So that's remarkable. This is a pulse sequence that is intrinsically robust. We're not doing any kind of encoding here. There's no fault-tolerant quantum error correction, no concatenation, none of that. This is just a certain trajectory on the ball sphere, which is impervious to these kind of errors. Okay, so we in this work did an exhaustive search over the space of URN sequences and up to, I think it was UR20. And what we found was by looking at the Bernstein-Vazirani n equals 10 problem, right? So this is 10 here refers to the length of the secret string. We found that UR14 was optimal in Montreal and UR18 was optimal in Cairo. All right, so the results that I'm about to show you, where we reran the Bernstein-Vazirani algorithm, but now with dynamical decoupling protection, is with these sequences implemented. So how did we implement the sequences? Here's the abstract circuit, and here is the cartoon of the actual circuit that was implemented. So the thing to notice is that for these superconducting qubits that IBM uses, the controlled NOT gates are much longer than single qubit gates. This is the time axis. So wherever there is a gap in the circuit, so we do a control knot here, and then this first qubit, the 0th qubit, has to wait around for the other control knots to happen. Wherever there's a gap in idle time, we insert a dynamical decoupling sequence. And schematically, I'm showing it as 4 pulses. In reality, like I said, it was actually the length 14 and length 18 universally robust sequences that we used. So the idea is extremely simple. Just identify gaps in the circuit, right, and insert a DD sequence wherever there is an empty gap. That's all we did. That's the only modification. Okay, so how well does this work? Here on the left is what I already showed you. And here on the right is what happens when we apply the UR18 sequence in the manner I showed on the previous. And immediately you see that there's a lot more green here. Right? Even at high Hamming weight, with lots of controlled knots, the success probabilities are much higher than over there. In fact, the average success probability goes up from 72 to 80%. Okay, so is this sufficient for quantum speed? And so it's all about the scaling. All right. Sense? Well, I wouldn't be standing here if the answer was not what you expected, right? So this is the quantum slowdown and quantum blowup that I already showed you without dynamical decoupling. Right? So the slope lambda should be less than 1, but in fact greater than 1. These are the slopes. Right? And with dynamical decoupling, we get these blue curves. So you see that now the slope for Cairo, it's with dynamical decoupling for Cairo, Montreal, For Montreal, it is, so let's look at Cairo first. So this blue is Cairo, right? And this is without dynamical decoupling, slow down. Cairo with dynamical decoupling, the slope is very, very close to 1. In fact, it's 0.98. And these are 2 sigma standard deviation error bars, so we can't really tell. But for Montreal, we went from here down to here. Right? And so this is pretty unambiguously within the error bars, the slope is now less than 1. Okay, so this is the unambiguous algorithmic quantum speed that I was talking about. In fact, you see that there's no blow up either, right? We went all the way to the largest possible problems. Even at size 26, we still got such we got the correct bit string, and so we're able to extract the slope and declare that on the Montreal machine, the one that had the higher quantum volume, the one whose 2-qubit gate errors were less, there is now an advantage relative to classic. Okay, so how much can we extrapolate? Can we extrapolate to asymptotic to arbitrarily large? Well, of course we can't, right? But that's because these machines end at 27 qubits. So who knows what happens beyond 27 qubits? And in fact, as I speak, I have a student who's now rerunning these experiments on the 127 qubit machines to see if we can observe to what extent we can observe the scaling. But I'm going to tell you about larger experiments in a moment in a different context. As far as these 27 qubit machines, this is as good as it's going to get in terms of getting to the largest, extrapolating to asymptotic side, because we reach the end of the machine, literally. The slope could probably be improved by further optimizing the error suppression here. And by the way, some of you probably are wondering, well, what about measurement error mitigation and zero noise extrapolation and all these other methods that are very popular nowadays? So we did use measurement error mitigation here, but it made an almost negligible difference. So all the work here is done by dynamical decoupling. Okay. So next, I want to talk about the second paper, which is work done with Pat, Victor, Jaewon, and Greg. And this is on the archive, and it's about an abelian hidden subgroup problem. And which one? It is Simon's problem. So Simon came up with an algorithm back in '97, which Peter Shor has reported inspired him to come up with his own factoring algorithm. And Simon's algorithm it's also an oracular problem. And the Simon circuit is written right here. It uses 2n qubits. What it is an algorithm that solves essentially a period finding problem. More specifically, it solves a problem involving a 2-to-1 function, which I'll define in a moment. And it solves it in order n queries, oracle queries. So this is the oracle right here. And this is another example, a very important, more important example, I would say, than the Bernstein-Vazirani problem, because it inspired Shor's algorithm, this one. Another example of an unambiguous algorithmic quantum speedup, an exponential quantum speedup, in the noiseless setting. Okay, so after the Bernstein-Vazirani demonstration, we wanted to see if we could do the same with Simon's algorithm. Okay, so let me tell you the twist that we have to introduce here. So here is Simon's problem, but it's again a game of finding a secret bit string of n bits. And again, you submit a guess to the oracle, and it returns, this time it returns a whole bit string. It doesn't return a single bit, it returns a whole bit string. So more specifically, we choose at random a function from bit strings of length n to bit strings of length n, and these functions are known to satisfy a promise. It's a periodicity promise. The promise is that for some secret bit string b, the function is periodic in this way. Okay, so for all x, f of x plus b is equal to f of x. And we'll exclude the b equals 0 string because that is not 2-to-1, that's 1. So now, with this promise, every player that plays the game can repeatedly access this oracle and submit guesses. Let's call the bit string x sub I, right? So I indexes bit strings. And let's say that you submit k guesses. Now, after you submit your k guesses, you can perform some side calculations. Basically, you have to solve a linear algebra problem on the side. You can do that on a classical computer. And for sufficiently large k, you're going to be able to figure out what the secret string b was. Okay, it's a simple exercise to solve this linear algebra problem. So the winner of the game is the player that is able to solve for b with the least number of tries, the least number of orbitals. We're going to call this the NTS, not the TTS, the number of tries to solution, close to the time. But in order for this to work on NISQ hardware, we had to introduce a modification, and that is we had to limit the Hamming weight of the secret string. So we're going to do this in the context of limited Hamming weight, or weight W Simon n, as we call this. So n is the number of bits, and the weight W is the Hamming weight of the secret strings, and we're going to limit W to be a constant. Okay, so now with that in mind, let's analyze the complexity of this algorithm. So what we're looking for is collisions. We're looking for two strings, x and y, where y is x plus the secret string b, such that f of x is f of y. Right? That's the promise. And we're looking for two strings that have this property. Once you find the collision, you've solved the problem. Right? And this is just like the classical birthday paradox, where you have, a party of n people, and you want to know how many hands do you need to shake before you find somebody who has the same birthday as you, and it turns out that you need to shake through n hands before you find somebody who has the same birthday as on average. So that's finding a collision. Okay, finding two strings. So this is the classical complexity of this problem. It scales like square root of n, where for us n, capital N is the 2 to the m strings. So classically, this scales like 2 to the little n over 2 is how many bit strings you're going to have to, how many calls you're going to have to make with the oracle. In the limited Hamming weight problem, where we fix the weight w, the number of possible strings is just the sum j goes from 1 to w of n choose j, right? And that's roughly n to the w. So it's a polynomial number of strings for a fixed w. This once you fix the Hamming weight, the problem is no longer exponentially hard. It's only polynomially in the weight w. Okay, so with that in mind, the number of tries to solution first in the original Simon's context, classically, like I said, it's 2 to the n over 2. Simon's algorithm solves this problem exponentially faster. So it's the log of this, so it's only order n. Okay, and in our limited Hamming weight context, now it's the square root not of the original 2 to the n, but it's the square root of n to the power w. So now the scaling, the classical scaling is polynomial n to the power Hamming weight over 2. And quantumly, again, it's the log of that. So now the quantum ideal noiseless scaling is w log n. Right? So it's a polynomial scaling versus a logarithmic scale in the limited Hamming weight context. All right, but we want to know, how is this going to scale on an ISK device? Are we going to get any kind of speed up? All right, so we're going to try it. And here are the results. So now we're talking about 127 qubit machines, the next generation. And here's the log of the number of oracle calls. The classical algorithm. We're optimizing everything, right? So we're giving the classical algorithm the best scaling that we know how to give it. There are some optimizations that can be done. That's why these classical yellow curves here don't look quite straight. But this is the scaling. The scaling is very close to half, which is what you would expect, right? The classical scaling is w divided by 2. So if you fit the log MTS, you expect that A, the factor here, to be half naively. In fact, it's a little less than that classically. You can do a little better. The ideal quantum scaling, if you could run Simon's algorithm on an ideal noiseless quantum computer, would be here. And if you actually run it on the Sherbrooke device, you get the red data here, which I can explain how we fit the curve here, but trust me, we're doing a fair job by fitting it, and we find a slowdown, unfortunately. All right, so this is for the Simon 15 problem. The bit string, the length of the hidden bit string is 15 bits. You need twice that many qubits. So now we're talking about 30 qubit problems encoded on the Sherbrooke device, and W is 6. And you see that, unfortunately, the quantum slope is worse than the classical slope. So again, it's a slowdown without dynamical decoupling. That's on the Sherbrooke device. On the Brisbane device, things are a little worse. We could really only go up to Hamming weight 5. And you see that the quantum slope is actually quite a bit worse than the similar case on Sherbrooke. Okay, so far, again, disappointment. No quantum speed up. But this is without dynamical decoupling. All right, so now we play the same game with dynamical decoupling. We insert DD pulse sequences into the idle spaces in the circuit. We optimize, and we find the best possible DD sequence. And what happens? We're getting a speed up again. All right, so now with DD, the blue curves, help me see this again. So the blue curve here is the new slope, and we are beating the classical scaling on Sherbrooke as well as on Brisbane. Right? And now you might ask, well, how does this behave as a function of W, the Hamming weight of the secret string? And that's what's shown here. So here is the slope as a function of W, the Hamming weight. The classical scaling is given here. Asymptotically, it approaches 0.5. This is on Sherbrooke. This is on Brisbane. Above the classical slope, that's a slowdown. Below the classical slope, that's a quantum speedup. So without DD, quickly, we get slowdowns. With DD, we're able to maintain a speedup. Same story, not quite as clean for the Brisbane device. However, we do run out of qubits here in the bad sense of the word. Right? So in the Bernstein-Vazirani case, we ran out of qubits in the sense that we exhausted the device. We went all the way up to 27 qubits. Here we have 127 qubits, but it turns out that for problem sizes greater than n equals 15, again, that's 30 qubits. Right? So for more than 30 qubits, we don't observe a speedup anymore. Okay, so I want to call this a demonstration of quantum speedup, but I have to be honest and tell you that what I would have liked to show is that we have a speedup all the way up to the size of 127 qubits, and that's not the case. So this is only up to 30 qubits is where we observe the speedup, and in fact, you see that for sufficiently large Hamming weights, the speedup does disappear. So this is kind of a mixed message. Dynamical decoupling, at least to the extent that we were able to optimize it here, was able to help. So whenever we constructed circuits that were deeper than had width greater than 30 qubits, we didn't see any speed up at all. So this shows you that the dynamical decoupling method is great, but it's not great enough. We are going to need quantum error correction ultimately. And certainly, if this is the case for Simon's algorithm, it's going to be the case for Shor's algorithm. If you're getting any ideas, hey, why don't I try Shor's algorithm? Well, those are much deeper circuits, and it's extremely unlikely that they're going to succeed. So some speed up, but not asymptotic. All right. So final topic, the third paper. This is not about an unambiguous quantum speedup. This is about a limited quantum speedup, and this is work done with Humberto Munoz-Balda, who's now a postdoc at NASA. And this is about a completely different topic. So the previous two problems were oracle problems. They weren't practical problems. Well, not that this will be a practical problem, but they were very contrived. They were designed by computer scientists who like to work with oracles. But in real life, we want to solve hard optimization problems, for example. Right. So this is going to be about solving a hard optimization problem. Not a useful optimization problem, but nevertheless a hard one. All right, and this is going to be using quantum annealing. So not circuit model, but using D-Wave. And let me just define quantum annealing very quickly. So in quantum annealing, what we do is we prepare an n-qubit system in the ground state of a transverse field Hamiltonian. Right? So the ground state is the superposition, the uniform superposition state. And then we evolve adiabatically according to two schedules. We slowly turn down the transverse field, and we slowly turn on an Ising Hamiltonian. I'll in a moment tell you what Ising Hamiltonian is, but this encodes the problem, the optimization problem. And then at the end, we measure all the qubits in the computation basis. And the adiabatic theorem tells you that if you do this slowly enough, so if you measure it long enough time TF, compared to the time derivative of the Hamiltonian norm and the gap of the Hamiltonian, the adiabatic theorem tells you that without decoherence, you're going to get arbitrarily close to the ground of the final Hamiltonian, the Ising Hamiltonian. Okay, and so the time to solution is going to the time to solution, which is the anneal time, so the final time TF divided by the success probability. We're going to get a quantum speedup if the time to solution for quantum annealing scales better with a problem size than the best classical algorithm. Right? And the thing is that this gap delta depends on the problem size, and for hard optimization problems, typically that gap is exponentially small in the problem size n, which means that your anneal time is going to be exponentially long. Or if you don't make it exponentially long, then your success probability will be exponentially small. Right? So, but for some problems, we can get polynomials instead of exponential. Okay, so what's the Ising optimization problem? It's encoded in this classical Hamiltonian, where you have control parameters H and J. H's are local fields, the J's are the couplings, and these are programmable parameters on the D-Wave device. So basically, the goal is to see if we can get an advantage, in this case, using the D-Wave problem, to solve this kind of optimization problem. Well, very quickly, history of the D-Wave devices. At USC, we got the first D-Wave device in 2011. It was a 128 20-qubit machine. And by the way, they use superconducting flux qubits, not transmons. And then 2 years later, we upgraded it to a 512-qubit machine. This is 2013, 512 qubits. Then another 2 years later, 1152 qubits. Another 2 years later, 2048 qubits, and now we have the D-Wave Advantage device, which has almost 6,000 qubits. Okay, so that's these are machines that are installed at 2 places currently outside of D-Wave, at USC and in Jülich in Germany. Very quickly, the old machines, pre the current one, had this so-called chimera graph. Each circle here is qubits. The lines are the connections between qubits. Each qubit had degree 6, meaning each qubit was connected to 6 other qubits. And now with the new machine, with the so-called Pegasus graph of the current Advantage generation, the degree is 15, and the number of qubits, like I said, is 5,760 in these devices. Right, so almost 6,000. Okay, so there has been a very long in optimization. The era between 2014 and 2021 used the previous generation machines, the ones that had the chimera graph. And as of 2022, we have this new generation with the degree 15, almost 6,000 qubit device. So I'm going to skip the entire history here because it was unsuccessful. There was no example of a speedup, no convincing example. There were claims, dubious claims, but there was no example of a speedup according to the criteria that I've defined before, a scaling. So in 2022, we did a fairly comprehensive study on the new D-Wave generation machines for so-called 3 regular 3 XOR set problems. All right, so these are hard optimization problems. They have a landscape that's very flat and it has exponentially many local minima. And I'm sorry to say the results were very disappointing. So this is the time to solution as a function of problem size. And so on a log scale, and you see a whole bunch of different curves here. The lower the slope, the better. Suffice it to say that the results in D-Wave were significantly worse than the rest. And I'm not going to get into the details of what all these other methods were, but all the other methods are classical optimization methods. So this was quite discouraging. So then we decided that we were looking at the wrong problem. Right? And so the paradigm shift is to switch from exact to approximate optimization. So for some reason, me included, everybody was locked into the looking for exact solutions to optimization problems, finding the exact ground state. But of course, the problem is that exact optimization really corresponds to the 0 temperature limit of quantum annealing. And actual quantum annealing hardware, as well as gate model hardware, operates at finite temperature. And of course, it's also susceptible to noise, decoherence, and control error. So let's look at approximate optimization. And now we need a new metric. So the previous metric, which was appropriate for exact optimization, which everybody used, was the time to solution, where we were looking at And the denominator, so this is the anneal time, and then the denominator is the probability of finding the actual ground state. So E0 is the energy of ground state. But for approximate optimization, we modify the metric. Instead, we're looking at what we call PT epsilon, time to epsilon. And so now the denominator is not the probability of finding the ground state, but it's the probability of an energy that is within epsilon multiplicative from the ground state. Okay, and epsilon is sometimes called the optimality gap. Right, so epsilon is, when epsilon is 0, it's exact optimization. When epsilon is some number greater than 0, then now it's approximate optimization. You're looking for an energy within a band. Okay, so we need an error correction strategy. Let me tell you that we have an error correction strategy for quantum annealing. Okay, and I'll be happy to answer questions about it. So let's skip through these slides. There's an error correction strategy, great. And we implemented it, and once you implement it, it involves an actual code. Okay, it's a repetition code, which you can decode by majority voting. It's basically a classical bit flip repetition code. So you decode it by majority voting. But it does more than just a classical bit flip repetition code. It also gives you an energy penalty against errors. That's really the unique aspect of this code. It penalizes errors that cause excitations. Well, the correction is just a classical error correction of a repetition code. It is also detecting errors, and errors that it detects, it penalizes. It gives them an energy penalty for them to happen. So they don't happen, they get suppressed. Now, once you implement this error correct, this code, so we're talking about logical qubits, and they happen in groups of 4, 1, 2, 3, and 4 here. So it takes the D-wave advantage graph, which I showed you earlier, and it turns it into a new logical graph, which has degree 5, no longer degree 16. Every circle here represents a logical qubit. Every logical qubit is 4 physical qubits here. And so we have a graph here that contains up to 1,322 logical qubits. So the experiments I'm going to report to you on are experiments involving more than 1,000 logical qubits. Okay, and we can get up to L equals 15. So L is the side length of the graph. Okay, so then we need to choose the right problem, and we're choosing a spin glass problem with the J's, the couplers chosen at random from this set, plus or minus these values here. There are reasons for choosing this. It's called a Sidon 28 set. I can explain why exactly these are the values that we're choosing, but these are hard optimization problems, and they form a spin glass. Finding the ground state is not something you can do in your head. At least I can, right? Unlike the solving Bernstein-Vazirani. All right, so what happens? Oh, yeah, one last thing. We have to benchmark against something, right? So what is the right classical benchmark? And spin glass experts know all about this algorithm, PTICM. It's parallel tempering, which is kind of a sophisticated way of doing simulated annealing. That's the PT. And then ICM is isoenergetic cluster movement. So it's a very souped up version of simulated annealing, if you'd like, PTICM. And it's the best in class classical optimization algorithm. Right? So we're benchmarking against the best. And we want to see if we can beat this classical algorithm, which is, as far as we know, optimal for these spin glass problems. Okay, so to the results. Here, I hope you can make it out from back in the room. Time to epsilon as a function of the number of logical qubits. This is a log-log scale. So this is all the way up to 1,300 logical qubits here. And what I'm showing are the PTICM results. So this best-in-class classical algorithm versus unerror-corrected quantum annealing. That's the U3. And error-corrected quantum annealing, where we implement this code. And here we have a quantum slowdown. Even though the quantum time to epsilon is, you see, orders of magnitude less than it took parallel tempering, right? But that doesn't matter. The fact that it's faster in an absolute sense is not the point. The whole point is scaling, right? Because you can always put this on a large cluster, and then you can shave off constant factors by just simple classical parallelization. So all we're about here is the slope. And unfortunately, when epsilon is 0.75%, right? So when the optimality gap is 0.75%, we don't see an advantage. We see a slowdown. The slope, quantum slope, d-wave slope is more than the classical. Okay, but now we go to a larger optimality gap, right? So this is less of a find the ground state. It's more of a solve an approximation problem. Epsilon of 1%. And now the classical slope is 1.93. The slope without error correction is 2.24, so worse. But the slope with error correction is 1.69. So we have a quantum speedup with quantum annealing correction, with this error correction strategy. And if we increase it a little bit more to 1.1% optimality gap, the situation is basically the same, but the advantage for the error corrected data has grown. 1.42 versus 1.1. And if we increase the optimality gap even more to 1.25%, now even without error correction, we find that the d-wave slope is lower than the slope of parallel tempering. Okay, so we finally have an example where using quantum annealing hardware, we're able to demonstrate better scaling. And the key was to move away from exact optimization to approximate. Okay, so let me wrap up. So we defined two problems: the single shot Bernstein-Vazirani and the weight W Simon that have provable quantum speedups without any conjectures, right? In the ideal case, and they're implementable on current hardware. And we demonstrated certainly for the single shot Bernstein-Vazirani, and with the caveats that I mentioned for Simon, an unambiguous algorithmic quantum speedup. And without dynamical decoupling, this didn't work. It was necessary to use dynamical decoupling. And then with quantum annealing, we demonstrated a limited algorithmic quantum speedup. Why limited? Because we don't know that parallel tempering with ICM moves is optimal. We don't know that. It's just the best currently available classical algorithm. Maybe somebody will come up with a better one. So in this sense of a limited speedup, we have an advantage for quantum annealing. We saw that errors and error correction matter, right? So certainly the results were better with error correction than without it. And the main caveat here is that exact optimization and even small epsilon, that is almost exact optimization, those remain hard for quantum annealing. And with that, I want to thank all my wonderful collaborators and you for your attention and patience.